All right, in this video we're going to talk motion graphs. Right, there are a couple different kinds of motion graphs. We're going to focus on two of them. The first is a position versus time graph. You can see on this standard graph we have position on our y-axis and we have time on our x-axis. Now, based on this, there's a bunch of information we can figure out about the motion of an object. First off, the slope of a position time graph tells you the velocity of the object, right? If slope is found by taking rise over run, the unit for our rise is in meters, the unit for our run is in seconds, so we see that the unit for that slope would be in meters per second, which is a unit for speed or velocity. So the steeper the slope, right, the greater the distance traveled in a time interval, the more gradual the slope, the less distance is covered. Right. Now, if the slope is curved, that indicates the velocity or the slope is changing. So if it starts out as steep and becomes more gradual, that object is going to be slowing down. If it starts out gradual and over time gets steeper, that means the object is speeding up. All right. So let's look at a couple different examples. First off, Cindy decides to go to a cow racing competition with Jim. Rank the cows from fastest to slowest. If I want to look at fastest to slowest, I want to look at the relative steepness of each of those slopes. I see that there aren't any numbers attached to this, so I'm just gonna use my best guess. But it looks like Elsie's slope is the steepest, followed by Bessie. Bessie seems to be the next steepest, followed by Dolly. And then finally, it looks like Moolinda has the most gradual slope, meaning her position isn't changing by a whole heck of a lot over that time interval, right? So she seems to be going the slowest. In this example, right, which graph represents an object that is speeding up and which is slowing down? So we see two very different looking graphs here, right? This one, the line starts near the origin at position 0 and gets further and further away from the origin. With this graph, we're starting out a decent distance away from the origin and getting closer and closer to 0, a position of 0 meters, right? But that's not the question, is asking which one is speeding up or slowing down. So here, looks like the slope is starting out a little more gradual and over time becoming steeper. That tells me this object is speeding up. Okay. Here, in this graph, right, it looks like the slope is starting out more gradual and, looks like it's becoming steeper over time as well, right? So even though the graphs look different, one is going away from the origin, one is going towards the origin, they're both speeding up, right? Now, if we were to look at a graph of something that's slowing down, right, on a position time graph, that would look more something like this, right? So we see in this type of graph, we're starting out steep, and then over time that slope is starting to level off. So that would be what a slowing down graph looks like. Let's do something with numbers. Maggie decides to go for a walk. After 4 seconds, she gets an urgent call and needs to turn around and meet up with her mom. So calculate her speed during each segment. Let's call this segment A, segment B, segment C, and segment D. So if it's a position time graph and I'm looking for her speed, that means I'm looking at the slope, right? So for segment A, right, it looks like she travels 5 meters in 4 seconds, which means she has a speed of 0.8 meters per second. Now in segment B, right, we see it's a nice flat line. That tells me that she got her call from her mom at 4 seconds, and she didn't leave that 5 meter mark for that entire 4 second time period. Right? So if we see a slope of 0, that means we have a speed of 0 meters per second. Right? Now with segment C, right, she's going from 5 meters to negative 30 meters. Right? So she's going a pretty decent amount of distance backwards. So the overall change in position there would be negative 35 meters. And she did that, she covered that distance in another 4 seconds. So the speed here would be negative 8.75 meters per second. And then in segment D, it looks like she hit that negative 30 meters and that stayed constant. So she wasn't moving for that 4 second time period. So in segment D, her speed is again 0 meters per second. What was her overall velocity? Well, remember, velocity is displacement over time. So if she started at the origin, if she started at 0 and ended at negative 30, right, her overall displacement was negative 30 meters. Again, it's a velocity, so we need that direction. And the time period was 16 seconds. So her overall velocity was negative 1.875 meters per second. How far from home does she end up? Well, it looks like if 0 is her home, she ended 30 meters away from her home. So that's the basics behind a position time graph. Let's look at a velocity time graph. So a velocity time graph is a graph of the slope of a position time graph. Right? So there are a couple things we can learn from a velocity time graph. First, area under a velocity time graph gives us the displacement of an object. And like the slope of a distance time graph tells you the object's velocity, the slope of a velocity time graph tells you the object's acceleration or change in position. So let's look at the different parts of a velocity time graph, right? Something that you can see is that a velocity graph will often look like this, right? Where the origin or the axis, the x-axis, will go right down the middle. The reason why we see that is because we have +1, +2, +3, and so on. And then below the axis, we have -1, -2. So all these negatives mean that the object is moving in the negative direction. It has a negative velocity. So if the line is above the axis, right, that means it has a positive velocity and the object is traveling forward. Okay? If the line is below the axis, that means that all the velocities are negative and the object is moving backwards. If the line is parallel to the axis, right, let's say I see a line like this, right, that means that the object is traveling at a constant velocity, right? So if this were to be my graph, right, the object would be traveling at 1 meters per second for the entire time period. If the line is getting closer to 0, right, let's say we're starting here and the line slowly gets closer to the origin. That means the object is starting traveling its motion at 2 meters per second and slowly getting to a motion of 0 meters per second. So as the line gets closer to 0, the object is slowing down. Now that could be getting closer to 0 above the axis or getting closer to 0 below the axis, because this just tells me it's moving at 2 meters per second backwards and still getting closer and closer to a velocity of 0. And finally, if the line is getting further from 0, right? So let's say it's starting at the origin and getting further from. That means it's starting out at rest and then moving at 1 meter per second and then 2 meters per second. So that object is speeding up. And again, just like the last time, that could be above the axis or below the axis, because in this case, it would be increasing its speed just in the negative direction. So let's do an example of this, and then we'll call it a day. From the following graph, find the acceleration during each of the segments of motion. So let's call this segment A, B, C, D, and E. So if I want to find the acceleration on a velocity graph, remember that's the slope. Okay. So in segment A, looks like the rise gets up to 30 meters per second in a time of 5 seconds. So the acceleration here would be 6 meters per second squared. During segment B, we see we have a nice horizontal line. That means that at this point in time, the object is traveling at 30 meters per second, and for that entire segment, it stays traveling at 30 meters per second. So that means that the acceleration, or the change in velocity, is 0. Let's look at segment C. So in segment C, it looks like the object is going from a velocity of 30 meters per second and slowing down to a velocity of 20 meters per second. So it has an overall change there of negative 10 meters per second in a time of 5 seconds. So the acceleration here would be negative 2 meters per second squared. So acceleration is a vector quantity. This negative tells me that it's slowing down rather than speeding up. But we'll get more into that later. At segment D, we have another straight horizontal line, slope of 0. So that means the object is not changing its speed during segment D. And if I'm looking at segment E, looks like it's going from a velocity of 20 meters per second down to a velocity of 0. So that would be negative 20 meters per second in a time of 5 seconds. So it's an acceleration of negative 4 meters per second squared. Now, if I were to find the overall displacement, right, I need to find area under the curve. To do that, I want to make a bunch of triangles and rectangles, right? Because I know that area of a triangle is 1/2 base times height, and I know that area of a rectangle or a square is just base times height, right? So I just want to segment this velocity graph into a bunch of squares and triangles. So I got one here, and then one there. Okay. So let's say in that first triangle, we have 1/2 times 5 times 30. Okay. And then in that green box, which is just a square, looks like my base is 15 and my height is 20. And then I got a couple red triangles and rectangles up there. So that first rectangle looks like has a base of 5 and a height of 10. The triangle right next to it, I'll take 1/2, base of 5, height of 10, and then that last little triangle all the way to the right has a base of 5 and a height of 20. So if I find that entire area, I get a total displacement of 500 meters. So that is the basics behind a position time graph. Please jot down any questions you might have, and we'll talk about them in class. Thank you.